Okay. Now, from this A matrix, we can take SVD, and our V is a 4 by 4, because we know last column of V, it is our P value. P should have homogeneous coordinates. That's mean capital X, capital Y, capital Z, and last one is 1. So it should be a 4 by 4 matrix. So the V is a 4 by 4 matrix, and the last column, okay, this is our values. This says X, Y, Z, and 1. These are the real world points. Okay, this is very important. And now if we check the values, okay, I will just clear the board. Naveen, what's the last value of P
Yes.
we expect? We have 4 values.
Yes. Yeah.
What's the last value we expect? We get 0.007.
It's 1.
It should be 1, right? Because in the
1. Yeah.
homogeneous coordinates, first one should be X, second one should be Y, third one should be Z,
It's
and fourth one should be 1.
1.
But it's 0.007. So we said, okay,
Yes.
if it is not there, then we can divide everything by the last value. So we'll divide it, and we'll see now. Okay, now it is 1. By the way, you can see it's a scientific number format. So we need to multiply this by 1000. Okay, then this becomes 1. Okay, and there was one more question. By looking at these values, he asks whether these values are in meter or centimeter or millimeter.
Millimeter.
Meter, I think.
No, because this is the Z, X, Y, Z. Z in the sense, this is your camera and this is your object, and you are looking in the front, and this is the front direction is Z, and this is your X, and the width of the object that is Y. Z is the how far you are from the object. Okay, so so we look at the values now again. The Z value is 1. So we need to multiply this with 1000. So we get 1463. This is the value we get, right? If it is meters, so this is like, like 1.4 kilometers away.
Yeah.
So this should be in millimeters.
Millimeter.
Sonu, you got it? Sonu?
Yeah, got it.
Okay.
Yeah, got it.
Okay. Now, when we return the values, we don't need to return everything. We can return only first 3 values because we don't care the homogeneous coordinates. Okay. Now the hard part of the lab is done. Yeah, I will run everything up to here. Okay. Now we take the norm between 0.4 and 0.5. So the 0.4 and 0.5 we'll assign into a variable called DRC tree, and we take the norm. That's mean difference between these two, 0.4 and 0.5. So 0.4 and 0.5, you can see it's this Rubik cube, the small one, 0.4 and 0.5. So what's Sonu, can you Google it and see what's the size of a Rubik cube? 3 by 3 Rubik cube.
3 by 3 size.
Yeah.
I think it can be 1 centimeter, I think. Total 9 centimeter.
Okay, let's see. We'll Google it and see. Size of a 3 by 3 Rubik, dimensional 3 by 3 Rubik cube. So it should be 5.6 centimeters.
Only that much.
Yeah. So we should get the same answer from here also. Yeah, we get 55 millimeters, 55.8. So that's been 56, right? Almost like 56. Yeah. So that's been 5.58 centimeters. So we get almost same answer. We got it, right?
Yeah.
And the other one, because even if it is tilted, it doesn't matter because we get the 3D coordinates now. So it can measure with the 3D coordinates exactly. That's the beauty of this. Even if it is tilted, still we can measure it.
Okay.
Because we get the 3D coordinates. Okay, what about 4 by 4 by 4 Rubik cube size. Other one is 4 by 4 Rubik cube. So it should be 6.7 millimeters. So we can measure it now. Rubik cube. Yeah, 6.4. Exactly, we got the exact value exactly. And the third one is 6 and 7. So the 6 and 7, this is that, you have seen this A4 papers, it comes in a big box.
Yes.
Yeah, so this is that box. So it's a cardboard box. So all the A4 bundles, it's inside this box. So this box should be little bit bigger than a A4 paper. So we can measure the size of A4 paper. So we can see size of A4. So it should be lengthwise, it should be 297. So the C7, C6 and C7, this should be little bit more than 297. So we can measure it. And okay, we had 307
Perfect.
millimeters. Yeah, it's correct, right? And the other one, the SP mean, it's 9 and 10. What is 9 and 10? 9 and 10. Okay. In this one, by measuring the center, 3 points, he said that's one. I mean, we don't need to know it. It's kind of lengthy calculation, but we can measure the size of this ball in that way. So I will skip that part because we don't need all of these things. But this is the idea of this lab. So we can measure 3D coordinates. Okay. So I will not go to the next part, but we can continue the next part. If you guys are not sleepy, I can continue, but otherwise I can continue tomorrow. But I will give a little summary. Up to now, we know how to calibrate cameras and how to measure a 3D point in the bird. So by having 2 cameras, we can measure everything in the bird. But the next one is to, one part of this lab is to the same, like the same object we need to measure by 2 cameras. So let's say you design a software to do this, but still these 2 points you need to measure by this image and the other image to get the camera coordinates. Okay. On the next part, we can measure only from one camera image. So we can write an algorithm to find it on the other side automatically. That is the next part. So one approach is to identify this corner of the paper bundle, and we can use that. You guys remember in the image analysis we had something called similarity image. We used it on yesterday also. So we use that patch and we search it everywhere on the screen, and we find what is the most similar place. So if we find it on entire image, so when we reach in here, so this, even though it's a little bit tilted, so this may come as the most similar image, right? So that's the one way to solve this problem, other than marking this the same point on both images. So let's say it's this Rubik cube in this corner. So one way to do is, okay, we need to measure the T matrix. We need to measure we need to get the camera coordinates from here and camera coordinates in here also by taking it manually. So other way is, okay, we can find a similarity image in the other one by measuring all the points and do it. And on the next part of the lecture, it's about, we don't have to search on entire image. So we can find something for one point in here. In the other side, it will be we will get something called epipolar line. So other than searching entire image, so we can search only on this image, only on this line. So that is sufficient. So right now, if we do it blindly, so one point in here, we need to search it on a 2D space. But other than searching on a 2D space, we can search on a 1D space. We can reduce the dimension and search it. Okay, shall we continue tomorrow, or what do you guys think?
We'll continue
Right.
tomorrow.
Tomorrow is better, right? Yeah, this is now
Yeah, that is better.
normal people are sleeping.
Sohan is almost.
Okay. Okay.